Hi, so now we start chapter 6. So simple linear regression. So simple means we only have the one variable to explain y. So at first, some notation and terminologies. So independent and dependent variables. So when we assume that a variable that depends on a variable x, so that means at least we would like to explain y by x. It doesn't mean x causes y, but the x explains y. So in such a case that we say x is an independent variable or predictor, and y is the dependent variable or response. Yeah. So for example, the x is the total calorie intake of a mouse, and y is the weight of the mouse. So x affects y, and it does not necessarily x affects y, but sometimes we would like to explain the y by x. So if a mouse takes more calories, then probably the weight gain is more. And another example in economics or finance, x may be an interest rate and y is inflation rate next year. Interest rate this year and the inflation rate next year. So interest rate affects inflation rate. Higher interest rate means less investment, so less demand, so lower inflation. So that is basically what the Federal Reserve does for the economy. And the third example, some engineering, the horsepower of a car and the maximum speed of a car. So more horsepower, the maximum speed is higher. So these are typical examples that you can see. The first one is biology or medicine, and the second one is economics or finance, and the third one is engineering. So these three are the major applications of statistics. Yeah, so for now, we use x and y both as lowercase because we want to reserve the capital letters for matrix representation of the model. Okay, so what's the simple linear regression? So that is basically assume a linear relationship between x and y. So we have data xi, yi for I is equal to 1 to n. So n is the number of observations, okay? And so this is the number of observations. So for example, the 100 individuals, then n is 100. And x, y, yi are numbers. So the x may be the calorie intake and y is the weight gain. So we have the 100 pairs of variables, observations. So that is the setting. And our assumption of the simple linear regression is yi is of the 1 and xi in some sense. So a times 1 plus the b times x1. But still we have some error because x does not totally explain y. So even the calorie intake is the same, but still the weight gain, the dependence such as mouse characteristics of the mouse, such as age or also some other environments such as temperature. And also just measurement error may exist. So we have some error. So that is the unique in statistics. Y is equal to a plus bx. You have studied in middle school, but we have the error term, epsilon I. Epsilon I is, called error. And if observed, it's called, residual. And A and B are parameters to be estimated. So before analysis, we don't know A and B, but we want to estimate A and B. So our objective is estimating A and B. And epsilon I is not observable, but once we decide A and B, then we can calculate epsilon I. So probabilistic interpretation. Okay, so A and B are constant, unobserved, but there is some truth. So one additional calories of so how much the weight, how much weight is gained when the mouse has 1 calories more. So we have some truth, A and B. And X is deterministic. So yeah, the calorie intake of the mouse is typical example. So we can, and we don't have any variability in X. So X is deterministic, so it's given. So even if some X is some random phenomenon, throughout this course, X is always deterministic. So X is just given number. We perceive X as deterministic. But epsilon is random, so that is natural. So it's error term, so it's random. So remember that Y is equal to A plus BX plus epsilon, and epsilon is random. So that means since other terms are deterministic, Y is also random. So random terms are Y and epsilon. Others are constant, but A and B are not observable. And X and Y are observable. So that is data. So that's observable. Yeah, and further, we assume some properties on error. So usually we assume the epsilon sub t or sub I. So we have several observations. So maybe t is equal to 1 to n or I is equal to 1 to n. And these are independent and identically distributed random variables with distribution, the normal, the 0 sigma. So often these assumptions are assumed. Sometimes more advanced model that drop most of these assumptions. The most important assumption is the error has mean 0. So that's why it's called error. If its mean is not 0, for example, 3, that is no longer error, right? So it's always the positive constant, so it has some effect. So error has mean 0. Yeah, so how to estimate the regression line? So suppose we points 1, 2, 3, 4, 5, then the regression line is determined so that this summation of epsilon I square is minimized. So epsilon I is the error size. So sum of the squared epsilon i's. So we minimize this quantity to determine this green line. So that is called the least square method. So this is basically the standard method to estimate the regression line. So maybe you have seen this kind of regression line in newspaper or some other articles, and this is determined by this rule. And how to estimate A hat and B hat? Later we will prove it, but here we have just some formula. So beta hat is estimated by summation. This summation is from I is equal to 1 to n. And this is also summation over I of this term. So the numerator is similar to the formula for covariance. And the denominator is the formula for variance. You can even put 1 over n minus 1 on both numerator and denominator. So covariance over variance. So that is B hat. And A hat is given by beta B hat and the X bar and Y bar. X bar and Y bar are just the sample mean of X and Y. So once you are given B hat, then X bar, Y bar is a kind of the center of the data. So it's at least the natural that the Y is equal to A hat plus B hat X that goes through the center of the data. So because the y is equal to a plus bx is a kind of trend line. So trend line going through center, that is a pretty natural phenomenon. And proof here, but a hat and b hat are given by this formula. And remember that we only observed several observations, and observations have some randomness, the epsilon I. So a hat and b hat are not exact truths, but just we estimate those truths. So a hat and b hat are different from a and b. So hat means the something similar to. So a hat is something similar to a, but it's not exactly the true a. You can see the Pizza Hut. It may not provide the true pizza. Yeah, so here is an example. So this is the data for 3-bedroom condo price in Detroit. This is from 2009, so 2010 maybe. So when I taught this class for the first time, I collected the real data. And I took the condominium price because in Detroit, there are many distressed houses. So if we use the single family houses, it's really not clear how the price is explained. So here I use the square footage and the price. And we have obvious positive these two variables, more square footage, then the higher price. Then we may assume that y is a plus bx plus epsilon. Then how to determine this line in our language? Then we can use the LM function. So at first we read the data. This is from the condo.csv file. And this data set only have the two variables, the price and the square footage. Square footage is given as an integer, but anyway, those are both numeric. And LM, y tilde x is the format. So linear model, the price on square footage. So this means the price is a plus b times square footage plus error epsilon. Then we get the result here and intercept and the square footage. Intercept is negative 265 and the square footage, the coefficient b is 0.2473, the a hat. So this is a hat and this is b hat. So this means y is equal to negative 265. This is the $1,000 plus the 0.2473x. So that means at first, one additional square footage, then price is $0.2473 higher. So one more square footage. $247.3 higher price. So intercept is the number when the number for y when x is equal to 0. So that means if 0 square footage, the price is equal to a negative $265,000. Okay, so this is a kind of nonsense, but you can imagine that the house has some property tax, and the property tax is never below 0, and usually at minimum 1,000 or 2,000. Typically. So that means if you have 0 square footage, you have to pay taxes. So probably the value is negative. So you can still interpret it in that way. So this is how to implement the linear regression, simple linear regression in R. And in a plot, you can make a scatter plot, then by plot function. And after that, you can add AB line function. So AB line function gives basically a straight line. So the format is basically AB line, AB. Okay, so then you can make this line. But this is the linear model. So another way is just to put the name of the linear model. Then automatically it takes intercept and the slope. Then it adds the regression line on scatter plot.